So today I want to talk about an application of symplectic topology to algebraic geometry. So the objects that we'll be considering are the following. So we're going to look at morphisms of smooth projective varieties over C. Okay, so we have some total space, Mbar. This is some smooth, complex Kähler manifold that lives inside of CPN. So in particular, this is a symplectic manifold. And we have some holomorphic map pi to P1. And this map is non-constant. So generically, this map is just a holomorphic submersion. So as we wander around generically inside of P1, we just get this holomorphically varying family of Kähler manifolds. And for a finite number of singular values, these Kähler manifolds degenerate into slightly more singular subschemes. So via his work on period domains, you get the following corollary of Griffith's work. So if one of these families has at most two singular fibers, then the variation of Hodge structures of this particular family is actually trivial. So a very naive interpretation of this is that from the viewpoint of Hodge theory, or sort of computable complex algebra geometric invariance, if these families have at most two singular fibers, then they essentially look and behave like the trivial family over P1. And so whenever you see some type of Hodge theoretic feature or triviality, the obvious question that always arises is whether or not it's the shadow of some type of algebraic cycles or geometric features inside of the space that you're dealing with, right? So you want to upgrade statements about algebraic structures to honest to God geometric structures. And so the result that I want to talk about goes in way of answering this. So if we have one of these families with at most one singular fiber, then we get two conditions on these families. First, they actually have to admit sections. So these are corresponding to these algebraic cycles that we're picking up. And moreover, for some family to fiber over P1 with at most one singular fiber, the family itself actually has to be uniruled. And so we're constraining the actual geometry of these families. And now when we allow for two singular fibers, we get a very similar statement. So let's suppose that we have a singular fiber over 0 on our sphere and another singular fiber over infinity on our sphere. And let's remove the singular fiber over infinity. So now this space sort of lives over C and it has some singularity at the origin. If we have that this family is now Claubiau, so the first Chern class vanishes, then we get very similar conclusions. So first we get that the space is again uniruled, and then we get that it actually emits a genus 0 multi-section instead of section. So it's a fairly simple exercise to show that as soon as you have two singular fibers, there are topological obstructions to actually producing sections instead of multi-sections. So the existence of this genus 0 multi-section is actually an optimal statement. So one remark that I want to make about this is that even though this is a symplectic seminar and my methods for proving this are very symplectic in nature, this really is a result that completely holds in the category of complex algebraic varieties. Okay, these sections and unirulings that are being produced are actually algebraic sections and algebraic unirulings, and not just analytic or holomorphic unirulings. Okay, so let me say a word about kind of what's the proof on the very high level. So the key input from Floer theory or symplectic topology is the use of a quantitative form of Floer cohomology. So I call this local symplectic cohomology, and in the literature, this is also sometimes referred to as relative symplectic cohomology. So the idea of this is to associate to every compact subset of a symplectic manifold M some chain complex. So the generators of the chain complex are constructed from the Hamiltonian dynamics near a compact subset K. Okay, so we're going to look at some Hamiltonian. We're going to look at its one periodic orbits, and we're going to find some way of just focusing on the Hamiltonian orbits that are nearby our compact subset K. And then in the usual sense in Floer theory, we construct differentials by counting pseudo-holomorphic curves inside of our symplectic manifold. So we apply this invariant to a very particular class of compact subsets. So what we do is we take our total family and we remove the singular fiber over infinity. Okay, so now this space M is just some symplectic manifold that's fibering over C. And the compact subsets that we look at are just the inverse images of disks. under our map pi. Oops, that arrow goes this way. And so what we show is that this local symplectic cohomology group vanishes for each one of these inverse images of a disk. And so if you look at the definition and the construction of local symplectic cohomology and unwind this vanishing in terms of your FLIR trajectories and algebra, what you find is that this vanishing of these local symplectic cohomology groups are actually vanished by the existence of holomorphic multi-sections over your finite radius disk. Okay, so using FLIR theory, we essentially produce these multi-sections or sections over some finite disks. Okay, but the statement is about sort of closed curves or sections over P1. So the other ingredient is a degeneration of the normal cone argument. So essentially we have some type of degeneration argument that lets us take holomorphic sections over the disk and degenerate them into holomorphic sections over all of P1. And so these are the two ingredients. We have FLIR theory to produce disks, and we have a degeneration of the normal cone argument to produce actual closed curves. And this is a very, very high level idea of the proof. So let me actually pause and ask if there are any questions before I try to discuss each of these very briefly.
Maybe I have a question. So your statement was purely algebraic geometric, right?
Yes.
And you are saying that you are using FLIR homology, so with all these perturbations and almost complex structures, in order to prove statement in algebraic geometry.
Yes.
Very interesting.
So we do all these perturbations and essentially we degenerate back down to the actual integral almost complex structure. And we degenerate out the Hamiltonian perturbation. We have some flavor of Gromov compactness that says that we still recover enough information to actually get an algebraic curve. Any other questions? Okay, so actually let me kind of add on to answering that question. So the first thing we need to do is actually arrange to be able to do FLIR theory inside of these spaces over C. So let's fix some notation. So M is just the complement of one of our singular fibers. So we always think of our singularities being over 0 and infinity. And we let M sub A just be this inverse image of a disk of radius A. Okay, so now M lives over C and M sub A lives over the disk. And so we want to do FLIR theory inside of this space M. And so in particular, we want to produce curves with respect to the integrable almost complex structure on M. So if we pick some arbitrary Kähler form that's compatible with respect to that integrable almost complex structure, it need not be convex or really amenable to doing FLIR theory on this open symplectic manifold. So the trick that we do to be able to do FLIR theory is the following. So we start with some Kähler form that's compatible with the integrable almost complex structure of interest. And we find some symplectic deformation or embedding of this Kähler symplectic form into some convex symplectic structure on this manifold. Okay, so we find some embedding into some completed or convex symplectic manifold. And to be a little bit more precise, we deform the Kähler form in such a manner that now we have an integrated maximum principle with respect to FLIR trajectories. Okay, the other nice property of this embedding is we have a very nice description of the Hamiltonian orbits of the radial function on our space M. So we take M, we now project it down to C, and we just take the norm. And if we look at the periodic orbits associated to this radial Hamiltonian, they just correspond to curves that wrap positively around the origin. Okay, so basically this is exactly the same picture that you get when you just look at the radial coordinate in C, but now your orbits upstairs are just covers of the standard orbits that you would get for the radial Hamiltonian in C. And so the first part of our strategy is the following. So using psi, we take the integrable almost complex structure that we care about, and we push it forward inside of this convex symplectic manifold. Then when we're in the convex symplectic manifold, we do FLIR theory to produce holomorphic curves, and then we pull back or trim these holomorphic curves along this bedding psi to get actual holomorphic curves for our desired integrable almost complex structure. Okay, so this is sort of a technical proxy. So let me now actually describe what is this local symplectic cohomology, this invariant that we're using to produce holomorphic curves. So let's take R to be this radial function where we project down and then take the radial coordinate in C. And we're going to consider the following sequence of Hamiltonians. So we're going to take an increasing sequence of Hamiltonians with increasing slopes. This is so we have some type of convexity. And inside our compact subset, M sub A, we assume that these Hamiltonians are C2 small Morse functions. And now the real key property that we care about is the following number 4. So if we have points that are inside our compact subset, so inside M sub A, we assume that the value of our Hamiltonian converges to 0. And if we're outside of our compact subset, then the value of our Hamiltonian explodes off to infinity. So if we're inside the compact subset, we go to 0. Outside the compact subset, we go off to infinity. So now we kind of apply the usual sort of machinery, and we associate to each one of these Hamiltonians some Hamiltonian flare chain complex. So here we take a copy of the Nabokov ring. So this is just Taylor series with exponents and non-negative real numbers. And for every periodic orbit, we take a copy of the Nabokov ring. And in the usual manner, we count rigid flare trajectories that connect pairs of our periodic orbits. And we assemble this into a differential in just the usual manner that we do with Hamiltonian flare theory. So how do we actually construct local symplectic cohomology? Well, given that H sub n is less than H sub n plus 1, we can take a monotone increasing homotopy between these two families, and we get an induced chain map that goes from the flare chains of H sub n to the flare chains of H sub n plus 1. And using these maps, we can now finally define local symplectic cohomology. So it's kind of this very complicated looking algebraic formula. So let's try to think about this in pieces. So what we do is we start with these finite dimensional pieces, these H sub n's, and then we take their colimit with respect to our continuation maps. So this produces some infinite dimensional complex. And then we take the completion with respect to our Nabokov parameter, or the valuation of our Nabokov ring. Okay, then we take cohomology and then we kill finite bars. So for the sake of this talk, we tensor with the Nabokov field. So I don't want to get into too much about what this is actually sort of algebraically saying or doing, and I just kind of want to focus on the heuristics and the properties that this complex has in our setting. So heuristically, this sort of complicated algebraic limit is just a way of killing the periodic orbits of our Hamiltonians that lie away from our compact subset M sub A. So this is the sense in which this is really a local symplectic cohomology theory. You're just focusing in on the Hamiltonian dynamics near your compact subset. Now, it is not local in sort of the sense that you are using differentials that can go anywhere inside your space. So we don't necessarily just consider flare trajectories that are inside our compact subset or something like this. Okay, so the key property for this local symplectic cohomology that we use is the following. So if the local symplectic cohomology of one of these inverse images of a disk inside of our symplectic manifold vanishes, then there exists a holomorphic disk inside of this M sub A that covers the disk of radius A. Okay, so another way to say this is we just have some multi-section over our disk of radius A. Okay, so how do we prove this? So the first key property that we derived for these local symplectic cohomology groups is a long exact sequence. So when we chose our H sub n's, we assumed that they were C2 small Morse functions inside our compact subset M sub A. So we have a natural map on the level of generators that just takes critical points of a Morse function and realizes them as one periodic orbits of our Hamiltonians. Okay, so we get this map on the level of generators. So if you're working in a Liouville domain, typically what you do is you say that you have an action filtration. And the action filtration says that the inclusion of the Morse cochains into the symplectic cochains is an actual subcomplex. And this is how you go about getting this long exact sequence. So the setting in which I am working, I am in a non-exact setting here. And so I don't necessarily have an action filtration. And so what I do instead is I just construct this filtration by hand using an integrated maximum principle. So we get some long exact sequence that's relating the cohomology of our space with this local symplectic cohomology of our compact subset M sub A. And one way that you can think about the cone, or the relating term in this long exact sequence, is it's some completed analog of positive symplectic cohomology. So we're really looking at Rabe orbits, or orbits that are wrapping around the boundary of this M sub A, and we're taking some similar completion for what we had before. So what we do is we make the following observation. So if local symplectic cohomology vanishes, then this says that the boundary homomorphism in this long exact sequence is actually an isomorphism. So if you unwind all the algebra that's involved in this, this tells you that there exists a Floer trajectory that's connecting a Rabe orbit, it's corresponding to a generator in this positive local symplectic cohomology, to a critical point of your associated Morse function. So in particular, I can just take the unit inside of cohomology. So if you kind of unwrap this, you remember that the Rabe orbits were things that wrapped positively around the boundary of our disk. And so particularly, this is saying that we can find some Floer trajectory that is covering the disk of radius A. So the vanishing of this local symplectic cohomology is witnessed by pseudo-homomorphic planes that are sweeping through points inside of our domain. Okay, so the rub is that these Floer trajectories are not actual holomorphic curves. So what we do is we consider a Gromov compactness argument, where we essentially take the value of our Hamiltonian perturbation to go to 0 on a compact subset. And we consider sequences of Floer trajectories associated to this degenerating sequence of Hamiltonians. This converges in some reasonable sense. The sequence of Floer trajectories converges to a pearl necklace, is what it actually converges to. And there's a piece of this pearl necklace that still gives us a genuine holomorphic multisection over the disk of radius A. And so this is the idea. Local symplectic cohomology vanishing gives us a pseudo-homomorphic plane that sweeps through our space, and then we turn off the Hamiltonian perturbation to get the actual multisection over the disk.
Excuse me, when you say Rabe orbit, you really mean some contact structure around, or you mean something more general kind of?
Yeah, so to be precise, the end of this M with this symplectic form is a symplectic mapping cylinder. Mm-hmm. So it's a Rabe orbit of a stable Hamiltonian structure.
Okay, good. Mm-hmm.
Yeah. So it's actually Rabe. Yeah. Okay, so I told you if this group vanishes, then we get these disks. So now I need to tell you why this group vanishes. So I'll try to say this very briefly and just try to hit the main idea. So the idea is to use an H principle by Mark-McLean. So what we do is we look at the singular fiber over 0. This is some positive codimension subscheme. And so by an H principle of Mark-McLean, this is stably displaceable inside of this total space M. So one of the defining properties of this local symplectic cohomology is that it vanishes for stably displaceable subsets. Okay, so using this H principle of Mark-McLean, we get that this local symplectic cohomology vanishes for some very, very small disk. Okay, but really we want this vanishing for every single compact subset. So we want it for all inverse images of disks. So what we do is we consider a rescaling isomorphism. We essentially rescale the dynamics on a disk of radius epsilon out to a disk of radius A. And we observe how this changes the local symplectic cohomology groups. So in general, this rescaling doesn't behave nicely with respect to the sort of completions needed to define this local symplectic cohomology. And so, these additional assumptions that we required on our space Mbar come into play. So to say one word, I use the vanishing of the first Chern class to get a grading on Floer cochains. And I use this to kind of as a technical crutch. Okay, so the final thing that I'd like to talk about is how we actually go from closed curves from these holomorphic disks. So let's consider a very, very naive picture. So let's just assume that our total space is P1, M now is C, and pi is the identity map. And so really, I just want to prove something tautological. I want to show that there exist holomorphic spheres inside of P1 from holomorphic disks inside of C. And so what we do is a degeneration to the normal cone argument. Okay, so we start with C times P1, and we do a symplectic blow up at the point 0 and infinity. So we take some ball, we remove the interior, and then we apply the Hopf map on the boundary of this ball, which is S3. So what this does is it produces for us a model for degenerating a sphere into a nodal sphere. So roughly speaking, as we have positive values or away from the origin in our C direction, we just get some smoothly varying copies of P1. And then as we degenerate to this singular fiber where we performed this symplectic blow-up, what happens in the Gromov topology is this smooth curve degenerates and bubbles off two pieces of P1. So one is this exceptional locus, and one is this sort of proper transform, this F0. Okay, so what do? Well, we take some very, very large disk inside of each one of our smooth fibers. So here I've just written some disk that contains the entire southern hemisphere and a little bit more. And we consider the Gromov limit of these holomorphic disks as we degenerate them into this singular fiber. And so you analyze what happens, and you realize that you get a nodal disk whose boundary is contained in one piece, namely this exceptional fiber. And you get some bubble that completely contains or covers this lower copy of P1. So we take a disk and we essentially stretch along the equator inside of C, or P1, and degenerate it into another disk along with a sphere. And so it's a very similar picture now for Mbar more generally. So instead of taking P1 and splitting it off into two copies of P1, what we do is we take Mbar and we split it off into two copies. So one is a slightly more singular family, and the other is some other family that is just in another copy of our Mbar. And so the idea is similar. We use these disks that we get from Floer theory, and we essentially degenerate them into pieces that have some sort of boundary in one of our split off pieces of Mbar, and then that have some closed components that completely cover our base P1, sort of the original copy of Mbar. So this is the very high level idea. But this picture sort of, in just the simple case of Mbar is equal to P1 is really the key geometric observation. We take disks and we split them off in this manner. So that's all I have. I think I'm 2 minutes over, so I do apologize.
Thank you very much. Any questions?
So this your local symplectic cohomology, how they are related to relative symplectic cohomology of Varalgonis?
Yeah, so this is just an extension of Omet's construction into an open convex setting.
So you are not doing cutoff of your Hamiltonians, right?
So I'm basically considering things where, like, I have my space, I have some compact subset here K, and this is the radial end R, and so I consider things that look like this, and then I have some radial end here.
I see.
So basically we do the exact same thing on our compact subset, but in the end we always deform to some radial Hamiltonian for convexity reasons. But there's nothing really special that I do that's different than Omet's construction.
And what does it mean that you introduce action filtration by hand?
Right. So in general, I'm working in a non-exact setting. So I don't have this sort of action filtration. So to construct this long exact sequence, I just by hand rule out the presence of Floer trajectories that would say that the inclusion of the Moore's critical points into the symplectic cochains is no longer a subcomplex, right? So kind of, you know, you have critical points inside, and then you have Rabe orbits, and you want to rule out Floer trajectories that have positive end starting at a critical point and go out to some Rabe orbit near the boundary. You always want, in my convention, to kind of go from right to left. So I just use the integrated maximum principle, or an integrated maximum principle, to rule out Floer trajectories going in the wrong direction. So in the case where...
So you just define, like, you look at the vector space spanned by the Rabe orbits, and then you just prove it's a chain complex, right? By just ruling out these.
So I look at the vector space.
So you sort of prove that the differential restricts into this subspace. Yes?
So I show that the differential restricted to the subspace of critical points is a subchain complex. And then I take the cone of the inclusion of the critical points into the symplectic chains to get this chain complex that's the Rabe orbits.
Oh, I see.
Yeah, so this is some quotient complex or mapping.
Okay,
complex.
okay. Yeah.
Yeah, so in the case where M is actually a Liouville domain, this essentially agrees with the action filtration. I mean, I won't
Yeah,
say
so you're just like taking the quotient with respect to being a critical point and not being a small action.
yeah,
Yes?
exactly.
Okay. Any more questions? If not, let's thank Alex again.